Hey, what's up, guys? So I got a new whiteboard, but unfortunately I don't have a project that's quite ready yet for a tutorial. So what I thought I'd do is try something new. In fact, I'm going to explain how RC filter circuits work in horrendous detail. Okay, so this is something completely new for me. I'm going to go off and ramble on and on about RC filter circuits for a while here. So let me know if this is beneficial to you or interesting at all. Okay, if not, I'll just delete this video and get rid of it. So let me know if this is a good thing or a bad thing. But basically, what I'm going to talk about, and let me just quick disclaimer: I'm not an expert on this. I don't have any notes. I don't have any references in front of me, so I'm probably going to get things wrong. I'm just going to kind of wing this, and the second warning, of course, is that I'm probably going to ramble on and on and on about unrelated things to this circuit. If something confuses me while I'm writing it, I might just go off on a complete tangent. No pun intended, because I will talk about trigonometry. So anyway, what we're talking about here is the RC filter circuit. And we have two circuits here. We have the low pass RC filter circuit and the high pass RC filter circuit. Now I'm going to assume that you kind of understand what I mean by low pass and high pass. Okay, we're talking about frequency input signals and what gets passed through and what doesn't. If you don't understand that, I think you'll start to grasp it as I go along. Like, for example, on your TV remote, when you push the button, you have an infrared transmitter, and then you have an infrared receiver on the TV, right? And when you push the button in, it's basically modulating the data within a 38 kilohertz signal. So it's like pulsing it at 38 kilohertz. And then on the TV side, it demodulates this and sort of filters it out, so it gets rid of all this high frequency stuff. So it might go through something that looks like this. So at the end of the filter stage, you'll end up with your data stream without all this high frequency crap in it, so that you can look at all those ones and zeros, right? So that's one example of an RC circuit. But trust me, these things are everywhere, and it's really important to kind of understand how it all works and how to get to those formulas. So we'll talk about things like, the output gain, the cutoff frequency, the negative 3 dB point, all that good stuff we'll talk about. So let's jump right in. I think we're not going to talk too much about the high-pass filter circuit, because in that case, if you understand how the low-pass works, it's pretty easy to take what you know here and apply it down here. So maybe if there's time, we'll talk about that. But I do have an example circuit on the breadboard here we'll look at towards the end. So I'll actually prove that my formulas work by applying them to a real-life circuit down here. So trust me, this should all make sense. So we're talking about putting an input signal on here. We're not talking about just a step change like a DC thing. Things that's easy, okay? We're talking about sort of repeating signals on the input here. So things like sinusoids and with all kinds of noise, things that are repeating that you can filter out. And the first thing I want to explain is what this circuit actually does. What does it do? So like if we apply in black here a waveform, this circuit can do two things to it. This is VI. This circuit can do two things to it. The first thing it can do to it is change the gain of this, or the amplitude, I mean. So what you put in might be a peak of 5 volts here, but you might only get 2 volts out. The second thing it does is it applies a phase shift to the signal. So I'll explain what phase shift is a little bit. So you might get something that looks like this on the output. So you see there's two things that happen to it. The first thing is that the amplitude changed. Okay, the second thing is the phase shift here. Phase shift is just a time delay. Okay, so it's a time delay from the input to the output, and it's represented in degrees. Okay, degrees. Okay, that sounds complicated, but if you think about it, this sine wave here is 360 degrees, and we know the frequency of it. Let's say that was 60 hertz, 60 hertz sine wave input waveform. Since it's 360 degrees represents 16.67 milliseconds. Okay, so then you can break it down by, once you get the degrees here, you can figure out what that time delay really is. And we'll do that, trust me, we'll do that. All right, let's look at this circuit for a second. What does the circuit really look like? Let's replace the capacitor with a resistor. Now what does it look like? It looks like a voltage divider, right? So if we had R1 and R2, and we needed to figure out what VO is, what is the output there? That's pretty easy to do, right? I mean, your current through R1 is equal to your current through R2, so that's pretty simple. You could just take VI and divide it by the R1 plus R2. Now you have current. Take that current, multiply it by R2, that'll give you the voltage here, times R2. And then that is equal to VO. Now, to get your gain, you always got to solve for the output over the input. So you could divide both sides by VI, and that's equal to gain. And you know, one thing that's always confusing when you talk about gain is you usually think of like it's gaining something up. But gain doesn't have to gain something up. It could also be a gain of less than 1, like 0.5. Multiply anything by 0.5. In fact, if we made this a 1K and a 1K, we take that 1 plus 1, that's 2. R2, 1. So it's 1 over 2. The gain is 1/2. That means anything we put here, no matter what frequency, we'll divide it by 1/2 there. Okay? So if we put a 5 here, we're going to get 2.5 volts out. Pretty straightforward. Now, what if we put that capacitor back here? Now, it doesn't divide everything it gets in by the same gain. Now, it's frequency dependent. So for high frequencies, the gain will be really small. So it won't gain it up at all. It'll be really small. So it'll hardly gain it up. For really low frequencies, the best gain it can get is 1. So it'll pass it straight through like it's there all the time. So no big deal. Like this doesn't even exist. And that's how the low pass filter works. So we could rewrite this. Let me get rid of some of this crap here. Let's get rid of R2 isn't in the circuit. We don't need to call that R1 anymore. Let me get rid of that. And this is C. So we have the RC circuit. But really, the C doesn't tell us really anything. What we're interested in is impedance here. Okay, so this is actually the impedance of C. In fact, this is even an impedance. It's Z of R. But before I rewrite this, well, I'll write it now. This is Z of C and Z of C. But what do we put in for Z of C? And this is where things get confusing, okay? You're going to have to follow me on this one and just push the accept button, okay? Just follow me on this. And this is, I'm going to try to use some analogies here to help you understand it and make it a little bit more intuitive, but it's not intuitive because now we're talking about complex numbers. We're talking about the imaginary plane, okay? It gets weird, but it all works out mathematically, and this is engineering, okay? This is an abstraction of the science and physics behind the circuit, so sometimes you just have to accept it and use it, okay? So impedance generally is made up of, it's a complex number. That means it has a real part, which is resistance, purely resistance, and it's also made up of a reactance, X. But right next to X has this funny little thing called an imaginary number, J. Sometimes it's called I, but in electrical engineering we use J because I would be confusing because we use I for current, right? So that wouldn't really jive well. So we pick J. And really, what is J? J is equal to the square root of -1. Okay, so it's weird. Things get weird here. But let's not I don't want to cloud you with trying to think of J. Maybe we'll loop back later on and we'll talk more about what J is. But when you look at this, what this tells you, these are coordinates. Okay, this is all trigonometry. This is a triangle, right? So let's just draw that. And then we have a vector here with some arrow there. But then we have an angle here of theta. I'm probably drawing this too small. Whatever. What we have here then, this would be our r down here, and then this would be our x. Sorry. X. So if we needed to find out the vector z, we would go r squared plus x squared, right? The Pythagorean theorem and all that crap. So that would be square root of r squared plus x squared, right? And then you have to give it some angle. So really z is a phasor and it has its angle and all that crap. We'll come back to this. I just wanted to sort of throw that out there right now before we get too into it. So here's what you have to memorize. X of c is equal to 1 over 2 pi fc. You have to memorize that. Just like you have to remember that the inductive reactance is equal to 2 pi fc. Not fc. FL. You have to memorize these things. Okay, there's no way to get around it. Okay? This all stems from the calculus and the hard number theory behind it, but we're not going to get into that here. But besides that would take possibly another whole nother video, at least a couple hours. So memorize these things. But for this circuit, we're only going to use the 1 over 2 pi fc. Okay. So what does that mean now? That means that this is equal to 1 over 2 pi fc with a j. In fact, yeah, I'm going to talk about this. This is something that always confused me about j. And here's an example of where I go off on a tangent on something. Sometimes with this, you're going to see the j in the denominator, and it'll be a positive number. And this always confused me, because sometimes you would see the j written like that, and then the 2 pi fc down here. So it's like, why is it positive when it's down there and it's negative when it's up there? Let me just explain. So j, like I said, is equal to the square root of minus 1. So if you had 1 over the square root of minus 1, you could multiply that. You could multiply that by 1, and you get the same thing, right? Or you could multiply it by square root of minus 1 over the square root of minus 1. Then that's like a 1, right? But what happens is this is then equal to minus 1 with the square root of minus 1, or is equal to minus j. You see how we get that? And by the way, this is 1 over j. So you see how we get 1 over j is equal to minus j. Just wanted to explain that real quick, because you guys might run into that. And I remember when I first saw it, I was like, what are you guys talking about? All right, so we got our z of c over here. In fact, what we're going to do is have this be a minus. Instead of a minus 1, it's going to be a minus j over 2 pi fc. Or this could be equal to x of cj. Could just do that. Don't do that. I mean minus. Z of c is equal to minus x of cj. Let's put that in. Minus x of c j. Oh, but get this. Okay. We could talk about this forever. The impedance of capacitance has no resistance, so it has no real part. Minus x of c j. It's purely reactive. And like I said, this is a triangle. So what that really is, if you look at the numbering system, and if this is like your x and this is like your y, then there is no x, but it goes straight down. So the angle is minus 90 degrees. Okay, so what you could write this as in the numerator up here is you can write the polar format of it which would be x of c with an angle of minus 90. Okay, just throwing that out there. We're going to leave that there. Hopefully that makes some sense. Okay, so x of c minus 90. Minus 90 degrees. And let's start simplifying this. Let's replace now the x of c, or I mean the z of c, with the actual reactants. Okay, so this is actually minus x of c j. This is interesting because what are we supposed to do with the j? How do we solve this gain? Well, really, the j, you can't do anything with this. You have to convert this here, this bottom part, into the polar format so that you have some magnitude. You know, you're trying to find that hypotenuse in the triangle. So right now you just have a mismatch of the coordinates. So what you have to do, these are coordinates right here. Okay, so if you have your triangle here, you're looking for this down here. And then this part here is r, and then this part here is the minus x of c. So what you do is that this becomes, I'll just do it real quick here. This becomes, we're solving for the hypotenuse. This becomes r squared plus, see, the minus squared becomes the plus, x of c plus, or squared, sorry. The angle of this, what is the angle of that? Is it minus 90? You got to think about that, okay? You got to think about what we actually have here. This is theta, the angle. What is the angle of theta? Well, we know that, we'll call this z here. Well, we know z, this is something I always kind of work out sometimes. So we know z's cosine of theta is equal to r. And then we know z sine of theta is equal to minus x of c. Okay, then you could actually solve for these things. So we know that r cosine, I'm just going to do a little bit of algebra here. R cosine of theta is equal to minus x of c sine of theta. And then I'm going to erase these guys here. Draw this back up here. And this is what I was talking about before. Then we could rearrange this and we could get sine up here. We could put r down there. Then we could go sine of theta over cosine of theta is equal to the, what was I doing here? Minus x of c over r. But then you should know this, that sine of theta over cosine of theta is equal to the tangent of theta. We want to solve for the angle though, right? We need an angle here. This is a vector. It needs an angle here. The angle then is the tangent inverse of this guy. Tangent inverse of minus x of c over r. Okay? This is getting good now, I hope. Okay, so what do we got here? Okay, we've got a gain. If you want to if you could strip the whole angle off, if you're only interested in the gain, let's just draw that. X of c over r squared plus x of c squared. That's your gain. So anything here I can multiply in here. Now what you do with x of c, of course, x of c is equal to 1 over 2 pi fc. That's all it is. Remember, the impedance brings in that j and all that goofy stuff. X of c is 1 over 2 pi fc. So there is your gain. The angle of this whole thing, or the phase shift, becomes minus 90. But then we have to combine these angles. So what you do is minus 90. Then we could pull this minus out and put it in front here, so that becomes a positive. Minus 90 minus the tangent inverse of x of c over r. Okay, there it is. That's the whole thing. That's how you solve for the gain and phase shift of the RC circuit. So that's pretty good. Just making sure that thing is still recording. 20 minutes. Not too bad, right? I need a sip of beer after that. But now we're going to talk about some interesting things. We're going to talk about a little bit of Bode plots here. So what we're going to do, let's strip all this crap off here. We can just get rid of all that here. Now what I want to talk about is the circuit. Now let's think about what's actually happening here. It's just like a voltage divider, but what happens is you have something like a Bode plot. And a Bode plot plots frequency or gain versus frequency. So it looks something like this, where this is gain, and this is a gain of 1 here, and then it falls down, right, in dBs, and don't worry too much about dBs. But at a certain frequency here, it just drops everything. Okay, so this is all low frequency here. It passes all this stuff, fine. But then at a certain frequency, it starts dropping. It just so happens that that frequency, when it starts dropping, is the minus 3 dB point. And what happens is, it's when this reactance starts equaling this resistance. So if we took this gain now, and let's make them equal to each other. So let's make a new term here. Let's make this term, I don't know, W. Everybody equals each other. What we can do now is combine these two in here. That becomes 2W squared. Okay, so that's good. The W squared can get pulled out now. So now we have a W out here. Oh, the W's divide. W. And then that equals 1 over the square root of 2. It just so happens that's our minus 3 dB point. Right at this point, when the gain is equal to 1 over the square root of 2, that's when this starts falling down. So that's when your reactance equals your capacitance, or your reactance equals your resistance in the denominator. That's when the gain starts falling. Now, this is interesting. This proves a lot of stuff, but what we want to figure out is how to design this circuit now. So you may hear something called the cutoff frequency. This is the cutoff frequency, but how do we solve for that? Well, I just told you it's when the reactance equals the resistance. So what we can do is go 1 over 2 pi Fc is equal to R. So what we can do now is solve for this. Okay, so let's multiply both sides by 2 pi c. Okay, that'll get rid of this crap, and then we left with RC 2 pi, like that. I'm just going to rewrite this term, and you're left with 1 over f. What is 1 over f? 1 over f is the period of the frequency, right? It's the time. What is this? We have a time constant now. Okay, so you might have heard something like that. So now you can solve for your frequency. Now, of course, what you can do, if you actually want to calculate this frequency at which it starts falling off, what that is equal to is 1 over RC 2 pi, or 2 pi RC, and then that is equal to f. That is your cutoff frequency. This is your minus 3 dB point. Okay, so what happens here, and they call this the minus 3 dB because if you go 20 log of 1 over square root of 2, that will equal minus 3 dB. Then, at this point, it starts falling at 20 dB per decade. So, 20 dB per decade, what does that mean? That means it's going to fall 20 dBs per 10 times of whatever your frequency was. So if this was like, I don't know, like 15 hertz, then it's going to fall at 20 dB per 150 hertz or whatever. Okay, so 20. I don't work with Bode Plots a lot. In fact, I hardly ever work in the dB or in the logarithmic scale. So I'm definitely not an expert there, but I calculate the cutoff frequency all the time. Okay, so basically that's it. I'm trying to think if there's anything else to talk about here. Oh, what do you think the phase shift is at when you're at the cutoff frequency? And this is kind of interesting. Well, what did I say the phase shift was at? What was the phase shift? It was like minus 90 minus the tangent inverse of x of c over r. What was that triangle? Remember, you got to think about triangles, something like that. But I said r is equal to c, right? So think about that. If r is equal to c, then this triangle has the same height and base lengths, right? So this angle is equal to 45 degrees. Negative 90 minus the 45 gives you a negative 45 degrees. So you know the phase shift at that point will be 45 degrees. So in your waveform, this is 360, this is 180, this is 90, this would be like 45 degrees. So your phase shift your minus 3 dB points your gain. So you're actually looking at something kind of like that at that point, 45 degrees phase shift. Okay, so that is the RC filter in horrendous detail. So I hope that makes some sense. Let's take a look at the scope and apply this now. Okay, so I just wanted to point out a little mistake I found in the calculations I was just showing you. And it's a tiny little thing in the phase shift calculation. So we had negative 90 degrees in the numerator, and then we had negative tangent inverse of x of c over r. Well, when you combine those two angles, you're supposed to subtract the numerator, you're supposed to subtract the denominator angle from the numerator angle. So it should have been negative 90 minus a minus tangent inverse. So those two minuses give you a plus. So the actual calculation is minus 90 degrees plus tangent inverse of x of c over r. Okay, so a little bit of a mistake there. In fact, I found that mistake by experimenting here on the breadboard, and I was actually trying to figure out the phase delay, and I was getting some crazy numbers because it was actually summing the negatives together. So I was getting like negative 100 degrees, and I was like, what? That doesn't make any sense. Not for these values. So, but anyway, what we have here is three circuits. We have a simple voltage divider, just purely resistive voltage divider, two 1Ks, okay, and we're measuring the V out, just like I showed you on the whiteboard. Then we have a 1K with a 1 microfarad capacitor, and then we have a 1K with a 10 microfarad capacitor, all low-pass filters here. My input waveform is a 60 hertz signal, okay? It's not the mains. I have it hooked up through like a little wall wart that divides it down, so I have here on the scope a 20 volt amplitude signal, so 20 volt peak, 40 volts peak to peak. In fact, let's zoom in a little bit on the scope. Okay, so hopefully you can see that. You might not be able to tell the colors apart, but you can definitely see the input. And right now I'm measuring the resistive voltage divider, so you can see that the voltage is divided perfectly in half. Okay, and you probably can't read the numbers here, but it is a peak of 20 volts, and then the second channel is hooked up to V out, which is divided perfectly in half. Okay, and you can tell that there is no phase shift at all. They intersect perfectly. And one way to do this is to jack up your volts per division, or lower your volts per division, and you can see that they're perfectly in phase with each other. Okay, let's bring them both back down to the same scale here. Okay, 10 volts, and then there we go, and bring that back. Okay, so they're perfectly in phase, but you are dividing it down, and it will divide it down for any frequency input. Now, let's go over to the 1K with the 1 microfarad capacitor. Now you can see the difference. You see how there's a little bit of there's hardly any gain difference, but there is a phase delay. What is the cutoff frequency for that? It's let's see, 1 over 2 pi. I actually have to calculate it out. 1e3 times 1e negative 6. And the cutoff frequency is about 160 hertz. So we're way under that. Okay, this is a low pass filter. So we're way under that. So the gain is hardly changed, but there is a phase shift. And I already calculated the phase shift out. And the phase shift is about negative 20 degrees. Okay, so that's what negative 20 degrees looks like. Now, I explained this before. The entire waveform is 360 degrees, and it's delayed by 20 degrees. So we know 360 degrees of a 60 hertz signal is about 16 milliseconds. So to convert the 20 degrees into time, we can just simply take 20 times the 16 milliseconds divided by 360. And we're left with milliseconds. And we'll be left with about 3.5, not 3.5, 0.9 milliseconds. And we can jack these way up here. And we can actually calculate this out. So I'm going to use my cursors now, and we can, oops, what am I doing here? We could figure out where that is. And it's telling me that the crossing is about 1 millisecond. Okay, so 0.9 is pretty close to 1 millisecond. So the reason there may be a little bit of error between our calculated versus the observed is because of tolerances. Okay, the resistor isn't exactly 1K. These are 5% tolerance resistors. The capacitor is electrolytic, so it's really bad for filtering. It's got a lot of ESL, which is equivalent series inductance, okay, which will affect the filtering capability of the capacitor. It also has a tolerance of 10%, which is pretty bad as well. So you roll all that in, and then you get the error, which really isn't that bad, right? So 1 millisecond versus 0.9 is pretty close. Now, I'm going to bring this back. All right, let's bring both of these guys back. Here, we'll bring both of their scales together, clear that up. And this is with a 1 microfarad and a 1K, okay? So this isn't too bad. The cutoff is about 160 hertz. So we're well under that. Let's now go to the 1K with the 10 microfarad capacitor. Wow. So look at that difference. Huge difference, right? So now our peak is only, let me zoom in a little bit here. Our peak is only about 6 volts. Okay, so our total gain is, remember, V out over V in. So our 6 over 20 is about 0.3-ish. Okay, I could actually probably get that a little bit better on here. So it's actually about 5.68. Just want to get a little bit closer, a little bit more accurate, over 20. That's 2.284 is that gain. So V out over V in. I already did the calculation. So X of C over square root of R squared plus X of C squared. That gain is 0.256. This 5.68 over 20 was 0.284. So that's pretty good. That's pretty close, actually. I think that's pretty good for just, 5%, 10% parts. So not too bad. The cutoff frequency of that, what is the cutoff frequency of that? 1 divided by 2 pi times 1e3 times 10e negative 6 gives me a frequency of 15.9 hertz. Okay, so we're way over that. We're way beyond that. So that's why when we bring both of these scales down side by side, that's why our gain has fell off so badly. So we're filtering that pretty well, actually. Now let's look and see what the phase delay is of this. Okay, where am I at here? Oh, we got to expand these up so we can get a better idea of the crossing points. Do the same to that. I went a little too much there. Bring these in a little bit. Okay. See, these are so out of phase that it's hard to even see where I'm looking at here. Okay, yeah, I'm getting lost here. All right, there we go. So we want to look at the yellow versus the blue. Now I can blow them up a little bit. I'm going to do this a little bit more slowly. Okay. So that's pretty good. Now we can even bring up channel 1 a little bit more. All right, now we'll use the cursors. And let's see if we can't figure out what that delay is. Versus B. Check it out. So we've got a delay of about 4.56 milliseconds. In fact, I think that's a little off. I don't think I'm quite at the crossing point. Okay, yeah, I was a little off there. Now I'll use my cursors here. Leave that one where it is. Bring that one in a little bit. There we go. 3.52 milliseconds is the delay. The calculated delay is 75 degrees. So I'll take 75 degrees times 16.67 milliseconds, divide that by 360, and what do I get? 3.5 milliseconds. So it's dead on. So that's pretty good. So 75 degrees is way beyond 45 degrees. Remember, 45 degrees would have been the cutoff frequency. So I forget what the cutoff frequency. So if we put 15, something closer to 15 hertz on here, then we would have seen that. So we're at 60 hertz, putting it through a 15 hertz or a cutoff filter, low pass filter. So anything under 15 hertz is going to pass. Okay. And that is low pass filter. So now, you can apply this. Sorry, I'm totally distracted by the scope here. So you can apply basically what we talked about here to the high pass filter. Okay, it's the same idea. You go through all the calculations the exact same way. And that's kind of what I'm trying to give you here. I'm trying to just give you another tool to put into your toolbox when you're doing circuit analysis. Okay, so that's pretty much it. I hope this helps. So, if this was too confusing or too fast or just kind of a dumb waste of time, let me know in the comments below. Thanks for watching.